All right, it's around 7 now, so we can start. So, hi all, I'm Chris Cho from Logistem, and welcome to today's AMCH review session here. We'll go over some harder problems from recent AMC8s, namely the final 5 from 2020 and 2019, and also the final 4 from 2018. So, first of all, can you all see my screen share here? Yes. All right, nice. So first, we have this slide here, which details some things about the test, and you can take a couple of minutes to look through this before we start to go through some problems. All right, so I'll stay on this slide for around a minute before we move on. So as for a brief overview, the AMC is for students in grades 8 or below, and it takes place once per year. And the format of the test is that it has 25 questions to be done in 40 minutes. And in each problem, there are 5 choices, A, B, C, D, E. And there is 1 point you gain for each correct answer and no points for each incorrect or blank. All right, then it's about time to begin. Let's take a look at our first problem, which is problem 21 of the 2020 AMC8. So as you can see here, here's the question. And also, let's go to the next slide so that we can see the picture as well. So in this question, it says that a game board consists of 64 squares that alternate in color between black and white. So as you can see here, this is an 8x8, and this is the regular chessboard coloring of this game board. And so this figure shows a square P at the bottom and also a square Q in the top row. So the square P is over here and the square Q is over here. So the problem says a step consists of moving the marker onto one of the adjoining white squares in the row above. So for example, if our piece is in this square over here, our piece can move here or here. And let's say if our piece is over here, our piece can move here or here. And also let's give one more example. If our piece was over here, then the only place it could move is diagonally to the left. So yeah, these are the possibilities for where our marker can move. All right, so yeah. All right, let's first draw out the region where our piece, our marker can move. So that is, our marker can go to any of the white squares that are in this grid. So we have these white squares, and as you can see, they kind of form a grid, a rectangular grid, except there are a few points missing. Like our marker cannot move to this square. If our game board were to be extended, this square would be a white square, but our board is not extended, so this square doesn't exist. So here we have a square that is kind of like deleted. All right. And similarly, we have these squares. to finish up our rectangular grid. So here, what we're actually doing is we're counting the number of 7-step paths that go through this kind of grid, but they don't pass through any of these 3 squares. And so one thing you can notice is that, first of all, in this grid, the only possible moves you're allowed to make, and these are the moves that are specified in the question, is that you can only move kind of like this way or this way. So you can't go backwards like this. And you're just gonna keep on moving kind of like right and up if you were to tilt this by 45 degrees. All right. So now let's count the number of paths that go through these lines. So one way you could do this is you can use complementary counting, which is the method of taking a total number and subtracting the number that you don't want. So for example, in this case, we know that there are 7 choose 3 ways to go from P to Q if we were just to go this way or this way without these restrictions that we can't go here. And then we want to subtract the number of ways that we do go here. So the number of ways that you do go here, we need to count those. So first, one thing you can notice is that if you pass through any of these 3 points, then you must pass through one of these. So that is, if you pass through this point, you must also pass through these 2. One of these 2. And so that's what's important. So we can ignore this condition that we can't go through this square because we know that if we pass through this square, we're also passing through both this and this. So, I have a question. So why 7 choose 3? So yeah. As for our rectangular grid, we have something like this. So if we tilt this whole thing, let's say clockwise by 45 degrees, you're gonna get a 3x4 grid that looks kind of like this. And one thing you can notice is that a move in this, a step consists of moving a marker to here or here, or let's say if you're going from here, you can go to here. So basically we're moving rightwards and upwards throughout this grid. So we're going from P to Q. Yeah. So this is why we have 7 choose 3, because this is exactly the number of ways to order 4 R's and 3 U's. So R's are for right and U is for up. And we can see that for every possible sequence of steps that go from P to Q, there's going to be a unique sequence of R's and U's consisting of 4 R's and 3 U's that basically contains the information that goes that this marker goes through. So for example, if we were to use the sequence RRRRUUU, that would be equivalent to going 4 steps to the right and 3 steps up. And so the total number of ways to order 4 R's and 3 U's is 7 choose 3, which is 35. So that's where 7 choose 3 comes from. And in general, if we have a m by n grid, this number of ways would be m plus n choose m, which is also m plus n choose n. All right, so okay, so now that we've found the number of ways total to get from P to Q, if these three points were allowed, we can use complementary counting. So we can count the number of ways we go through this point or go through this point. And so first, let's count this. So the number of ways we go through this point when traveling in a path that goes rightwards and upwards, so that's this point, is, so first, you must go 3 steps to the right before going anywhere because you have to get to this point. And then afterwards, you have 4 ways to get from this point to Q. And so in this case, there are 4 possible paths. And in our other case, let's say we're going through this point, there are 5 ways to get from P to this point because you can go here, 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 or here. And there's only one way to get from here to here because you can't go left. So in total, there are 5 paths that go through this point. And when we add these two together, we'll be overcounting the number of paths that go through both this point and this point. So the number of paths that go through both this point and this point are, this number of paths is going to be 2 because the 2 paths are going from P to this point, to this point, to this point, and then to Q, or going from P to this point, to this point, to this point, to Q. So there are 2 paths that pass through both. And so here we can count the total number of paths that go through one of these 3 points to be 4 plus 5 minus 3, or sorry, minus 2, which is equal to 7. So here, in this count, we're including 7 paths that go off the grid. So we wanna get rid of these 7 paths, and this gives us a final answer of 28 paths. So the answer is A. 5 plus 4 minus 2. Okay, so the reason we have 5 plus 4 minus 2 is because there are 5 ways to go from to have a path that goes from P to Q and passes through this point. And there are 4 paths that go from P to Q that pass through this point. And there are 2 paths from P to Q that pass through both of these points. So so in total, the number of paths that go through a point that does not exist on the board is going to be the number of paths that pass through this point, which is 4, plus the number of paths that go through this point, which is 5, and then minus 2, which is the number of paths that go through both. All right, we have another question. What about the point that's on the bottom left corner? Bottom left corner. Oh, this point? Okay, so since we're only moving upwards, and so we're only going to go here or here on each move, we can see that we can't get there because if we were to get there, we have to either we have to go kind of like backwards, and that's not allowed. And also, if we go this way onto this square, we won't ever be able to get to Q. So that's why we're confined to this rectangular grid. The bottom left corner. So like we can't since we can only go this way in this direction or in this direction, we're never going to be able to get past any of these points. So we can't get to any of these points. All right, are there any other questions? Okay, so if there are no more questions, we can move on to our next problem, which is problem 22 from the same year. So in problem 22, we're given this machine where a positive integer n is fed into it and an output is calculated according to this rule. So we're asked when the same 6-step process is applied to a different starting value of n and the final output is 1, we want to find the sum of all such integers n. All right, I see some ideas in the chat. So this is the awesome function. Yes. Yeah, collapsed conjecture. Yes. So this problem is related to the collapsed conjecture, but you don't really need to know anything about the collapsed conjecture to solve this problem. The key idea is to go backwards, to work backwards. So we apply this 6-step process and we'll reach 1 by the end. We want to find basically the sum of all integers. You want to find all integers that go to 1 within 6 steps, or rather in exactly 6 steps. So one way you can do this is by, so as I said, working backwards. In our last step, our 6th step, we're going to end with 1. So we're going to end with 1, and one way we can approach this problem is to see what can go to 1. So we're basically inverting the function, but not exactly, since there are more than one. There are sometimes more than one possibility for what can go to a certain number. So if on our 6th step, we get 1, then on our 5th step, we must have gotten 2, because we're either going to have something such that 3n plus 1, some number n such that 3n plus 1 is, and also n is odd, and we can see that's impossible. So in fact, the only possibility for what the 5th step, what we got for the 5th step is 2. And on the 4th step, the only possibility for what we could have gotten is 4, because 2 cannot be written as 3n plus 1 for an odd number. And you can continue working backwards. So for 4, you could have gotten h or 1 for our 3rd step. On our 2nd step, if we got 8 on the 3rd step, the only possibility for what we got on the 2nd step is 16. You can check this because h cannot be written as 3n plus 1. And since we already showed that if you got 1 on the 3rd step, you must have a 2 on the 2nd step. We've basically seen this already. And also, our 1st step, our output must have been either 32 or 5. If on the 2nd step, our output was 16. And we can draw the same chart down here. And lastly, these are the possible values for n in the last column rather. So in the last column, we can notice that the only way to get to 32 is by having 64. The only way to get to 5 is by having 10. And also the only ways, or rather the 2 ways to get to 4 are listed here, 8 and 1. So these are the 4 possibilities for what n can be. And so we can actually check that since we have this kind of tree thing, these four numbers all get to 1 on the 6th step, and there are no other such integers n. So we can add up all of these n's. So their sum we can calculate to be 83, which is the final answer, and we're done. All right, so this is problem 22 of the 2020 AMC 8. If there are any questions, if there aren't any questions, we can move on to the next problem. All right, I haven't gotten any questions, so let's move on. So this is problem 23. 5 different awards are to be given to 3 students. Each student will receive at least 1 award. We want to find the total number of ways the awards can be distributed. Okay, so we have some ideas in the chat. We have stars and bars and also casework. So let's try some casework since there aren't many cases in this problem. So let's say our 3 students are A, B, and C. We know that students are distinguishable, so we won't have to worry about indistinguishability. So the possibilities for what each student began with are, so we can have 1 person, 2 people having 1 candy or 1 award, and 3 people, 1 person having 3 awards. So there are 3 ways to do that. And the other possibility, the other 3 possibilities are having 1, 2, 2, 2, 1, 2, or 2, 2, 1. So these are the number of awards that each person got. And so we can count the number of possibilities, the number of distributions for each case. In our first case, we have A having 1 award, B having 1 award, and C having 3 awards. So the number of ways we can count this is we can first give an award to A, and there are 5 possibilities for which award we give to A. And then, so A's gotten its award, and then B gets the award in 4 ways, since there are 4 ways remaining, or there are 4 awards remaining. And then once we have given A and B their awards, the 3 remaining awards just go to C. So this is the total number of ways to count the award distributions in this case. So that gives us 20. So there are 20 distributions in our first case. And since the second case and the third case are symmetric, there are also 20 ways to distribute the awards in the second and third case. And now we're on to our fourth case, which is when 2 people have 2 awards and 1 person has 1 award. So the number of ways we can count this is, first, we're going to give 1 award to student A, and there are 5 ways to give an award to student A. And then we can give 2 of the remaining rewards to student B. So we're going to be choosing 2 of the 4 awards to give to student B. So there are 4 choose 2 ways to do that. And then once you've given A and B their awards, student C gets the remaining awards. So in this case, there are 5 times 4 choose 2, which is 5 times 6, equals 30 ways to distribute the awards. And the last 2 cases are symmetric, so we can write 30 for those. So now we've gotten through all cases, all that remains is to add up the cases. And this number is 150, which is the total number of ways to distribute the words. Oh, how did I get the cases? So we're casing on like which student, the number of awards that each student got. So for example, since each student received at least one award, the only possibilities for the number of awards of each student are 1, 1, 3, and 1, 2, 2, because these are the only two ways to partition 5 into 3 positive integers. And so then we've gotten our cases, which are having 2 people having 1 award and 1 person having 3 awards, and then also having 2 people having 2 awards and 1 person having 1 award. So then we can order these, and these are our cases. All right. How can you get 20 ways for 131? Oh, so in the case of 131, we're basically shuffling the people. Since in our first case, we have 1 person having 3 awards and 2 people having 1 award. And in the second case, it's the same deal, but instead we're kind of having B and C swapped. So instead of B having 1 award and C having 3 awards, we have B has 3 awards and C has 1 award. So in fact, the number of ways to distribute this is going to be the same as the number of ways to distribute this in the first case. So we also have 20 ways in this case and 20 ways in this case. And a similar reasoning holds for these 2 cases. One last question. What is 4? So, in this case, the reason we have 5 times 4 is because, so we want to distribute these awards to these 3 people so that A and B have 1 award each. So first we can distribute one of the awards to A, and there are exactly 5 ways to do this because we have 5 awards total and we're giving 1 to A. And now we've given A its award, so we want to give B its award. So for B, we have 4 remaining awards to choose from, and we're going to give one of them to B. So there are 4 ways to choose an award for B. And then the remaining 3 awards go to C. So there are totally 20 ways to distribute the awards in this case. All right, no problem. So next up, we have problem 24 from the 2020 AMC. There is a diagram for this picture, so I'll go on to the next slide where the diagram is. Oh no. All right, so in this question, we have a large square region that is paved with n squared base square tiles, and each of these tiles measures s inches on a side. So here we have a bunch of s by s squares, and in fact, there are n squared of them arranged in a n by n grid. So for each tile has side length s, and also the distance between each tile. So this distance, each of these distances measure d inches. So we have d inches here, of here, and also s inches on each of these squares. So we're told that in the case of n equals 24, 576 gray squares, gray tiles cover 64% of the total area. So let's try to make this into an equation, since we have two variables, s and d. So we want to find the ratio d over s. All right, so if you can imagine this total square region that goes through all 576 gray tiles, you're going to notice that the total side length, this side length over here, is going to be, we're going to have the length of 24 gray tiles, which is 24s. And then we're going to have 23 sections of length d in between, and then 2 on the sides, so plus 25d. These 25 are just the distances between the tiles, and also the distances between the edge tiles and the edge of our square region, large square region. So this will be the total side length of our large square region. And we're told that 64% of the area of this large square region is equal to the total area of all 576 gray tiles. And so we can write this as 576s squared, which is the total area of all 576 gray tiles. This is equal to 64% of all of the area of the large square region, which is 24s plus 25d squared. All right, so does everyone understand what we have so far? All right, so I haven't gotten any questions yet, so we can move on. So we have this equation, and we want to find the ratio d over s. And we can notice that we can actually find it in this equation because we have all the information necessary. So to simplify our calculation, let's write all of these numbers as perfect squares. So then we can take the square root of both sides and not have to deal with any weird quadratic equations. So we can rewrite 64% as 64 over 100. And now that we have this equation, we can take the square root of both sides. So if we take the square root of the left side, we have 24s. If we take the square root of the right side, we have 8 over 10 times 24s plus 25d. And now we can find d over s. So this stuff becomes 24s is equal to 4/5 times 24s plus 4/5 times 25d. And we can just kind of solve this thing. So we can calculate d over s to be from here we can calculate d over s to be 6 over 25. Yeah. All right. So now we've calculated d over s to be 6 over 25. So our final answer is A. All right. So are there any questions for this? If not, we can move on to our next problem, which is the final problem of the 2020 AMCH. how did you get the last equation? Oh, this one. So for here, we can rewrite this one. Okay, so let me just write something that's a bit easier to understand here, probably. So once we get to this equation, what we want to do is to solve, basically solve for s in terms of d or d in terms of s. So we can multiply both sides by 5/4 to get rid of all the fractions. So if we take the left-hand side and multiply that by 5/4, we have 30s. And when we multiply the right-hand side by 5/4, the 4/5 cancel, and we're left with 24s plus 25d. And now we can move 24s to the other side to get 6s equals 25d. And then when we divide both sides by 25s, we're left with 6/25 is equal to d over s. And so 6/25 is the final answer. Yeah, no problem. So the main idea here is that when you get to this equation, all that remains is to solve for s in terms of d. So in fact, you can divide both sides by s here, and you're gonna get a linear equation in terms of d over s. So you can also do that. So I guess the key point here is that once you get this equation, you can find d over s. All right. So since there are no more questions, we can move on to problem 25. Okay, so just algebra. All right, so we're gonna do what we're gonna do here is pretty similar to what we do in an algebra problem. We're gonna give all of these side lengths basically a variable. So we're gonna give a side length, a variable, to square s1, and we're gonna say this is a1. We're gonna give a2 to the side length of s2 and a3 to the side length of s3. So here we have basically all of these rectangles, and also the other basic piece of information that we've gotten is that the side length of this length, the width of this rectangle is 3,322 units, and the length is 2020 units. And so this is all of the information we've gotten. And now we want to make some equations. So first, how can we use this condition? All right, so the way we can use this condition is by writing this number as the sum of some lengths. So in particular, this number is going to be the sum of this length and this length. So it's going to be equal to a1 plus this length, which is also a2 plus a3. So this is our first equation. Our second equation is 2020 equals, in this case, we have this length, which is a1 minus a2, plus this length from here to here, which is a3. And so now we've written our equation, and we've also exhausted of all information given. All right, so what that means now is that we need to start solving the equations. So we want to find a2, which is the side length of s2. So the way we can find a2 is by noticing that if we subtract these two equations, so if we subtract the second equation from the first, so rather equation 1 minus equation 2, we get that the difference 3,322 minus 2020, which is 1302, is equal to 2a2. And so a2 is equal to 651, which is our final answer. All right, so the answer is A, and we're done. All right, so I haven't got any questions yet. If you have any questions, you can ask them in the chat. And if not, we can move on to the next year, which is 2019. Okay, so now let's move on to the 2019 AMC 8. And we'll start by doing problem 21. So in problem 21, we have a graph of a triangle formed by 3 lines. So that is, we're going to draw our coordinate plane with our X and Y axes. And we're going to draw these 3 lines. So first, drawing y equals 5 isn't that hard. We're going to take this point and we're going to draw a horizontal line. And then we're going to draw the lines 1 plus x, sorry, y equals 1 plus x and y equals 1 minus x. So we can write these both in slope-intercept form. So this is equal, this equation is the same as y equals x plus 1, and this equation is equivalent to y equals negative x plus 1. And so one thing you can notice is that both of these equations pass through, both of these equations have y-intercept at 0, 1. We can draw this y-intercept. And then we can draw the 2 lines which have slopes 1 and negative 1. And they're going to make 45-degree angles. And so we've now drawn this region, which is given by the problem to be a triangle. And in order to find the area of this region, we just want to find its base and its height. So if we let this be its base, we can notice that the base has side length 8. Yes, it is isosceles because it's actually a right isosceles triangle, because these 2 lines that go through this common point at 0, 1, they have slopes 1 and negative 1. So in fact, these 2 lines are both perpendicular, and also they both form 45-degree angles with the y-axis. Yeah. So we can notice that the height is which is basically this length on the y-axis, is 4 units. And then by our 45-degree angles here, we have a 45-degree angle here, 45-degree angle here, and a 90-degree angle here. We have a 45, 45, 90. And so this length is also going to be 4, and so is this length. So to find our area, we'll just do half times base times height, which gives us a final answer of 16. So the answer is E. Oh, how did you find the area of the triangle, the height of the triangle? So in order to find this height, we're basically finding the length between here and here. And this top point has coordinates 0, 5. So this point has coordinates 0, 5, and this point has coordinates 0, 1. This is the common y-intercept of these two lines that we were talking about. And then the point on the base of this height is going to have coordinates 0, 5, because the point at which y equals 5 intersects the y-axis is 0, 5. So yeah, the distance between these 2 points is just 4. All right. So are there any more questions? Okay. So how long is this? This will probably go on until we finish all 14 problems that we're gonna discuss today. And this will probably end at around 8:30. So if you want to leave, you can leave whenever you want to. This is being recorded, so you'll be able to see the recording. 8:30 Eastern Standard Time. 8:30 EST. All right, so let's move on to the next problem, which is problem 22. So in this problem, we're told that a store increased the original price of a shirt by a certain percentage and then decreased the new price by the same percent. We're told that the resulting price was 84% of the original price. And then we want to know the percent that the price was increased and decreased. Yeah, Eastern Standard Time. The recording of this entire thing will be posted on YouTube at the Logistem YouTube channel. Okay, so for this problem, I see a lot of answers already. It's great. Okay, so we're told that the price of this shirt was increased by a certain percentage. We're going to say it was increased by X%. And then it was then decreased by X%. So now we have a new price, which is 84% of the original price. So let's say that our original price was P. Then after increasing the price, we're gonna multiply by 1 plus X% to our original price. And then once we've multiplied 1 plus X% to the original price and gotten our increased price, we're going to decrease it. So now we're multiplying by 1 minus X%, since we're decreasing the new price by the same percent. So this is going to be our resulting price. We're told that this resulting price is 84% of the original price, which is P. So now we want to find X. So we can see that we can cancel out P because it shows up on both sides. And also, we can rewrite this equation, this left-hand side, as a difference of squares. So 1 minus X% squared is equal to 84%. And by percent, I mean x over 100 would be x%, and 84 over 100 would represent 84%. So for 1, we can write this as 100%. And we can rearrange this equation to get x% squared is equal to 16%. And here it might be a bit clearer to write this in terms of fractions. We can take the square root of both sides to get x over 100 is equal to 4 over 10. And this gives x equals 40 as our percentage of increase and decrease. All right, so are there any questions? If not, we can move on to problem 23. I found these easy. All right, so anyways, so we can move on to problem 23 now, since I haven't seen any questions. So this is problem 23. After Euclid's High School's last basketball game, it was determined that 1/4 of the team's points were scored by Alexa, and 2/7 were scored by Brittany. And also we're told that Chelsea scored 15 points, and also that the other 17 members all scored at most 2 points. All right, so we want to find the total number of points scored by the other 17 members. Okay. Team members should be replaced. All right, so in this problem, we're told that 1/4 of the team's points were scored by one person, and 2/7 of the total number of points scored by the team were scored by another person. So what this tells us, this piece of information tells us that 1/4 of the team's points is a whole number. So what this means is that the number of points scored by the team, let's just say n is equal to the total number of points, total points. Then, since 1/4 of n must be a whole number, n has to be a multiple of 4. And similarly, since 2/7 of n is a whole number, n must be a multiple of 7. So in fact, n is a multiple of 28. And now, one thing you could do from here is to guess and check, but let's try something that's a bit more rigorous. So we're told that these 3 players scored this many points, and then we want to find the total number of points scored by the other 17 members. So one thing we might think of is, how can we find the total number of points scored by the other 17 members in terms of n? So as for this, here's something that we can do. We can first notice that Alexa scored 1/4 n points. Brittany scored 2/7 n points. And Chelsea scored 15 points. And so now what this leaves is for the other 17 members, is that they scored 1/4, n minus 1/4 n minus 2/7 n minus 15, because those are the number of points scored by the other team members, or rather the team numbers A, B, and C. And so we can calculate this expression to be 13 over 28 and minus 15. And we're told that each of these 17 members scored between 0 and 2 points. So in fact, this number of points is between inclusive 0 and 14. We can rewrite this expression as, or this inequality as, 13 over 28n is between 14 and 29. And since n over 28 is an integer because n is a multiple of 28, this number here is 13 times an integer. So it's a multiple of 13. So the only multiple of 13 that occurs between 14 and 29 is 26. So this number must be 26. So now we know that 13 over 28 times n is equal to 26. From here, we can find out that n equals 56, but we actually want to find the total number of the total score of the other 17 members, which we've calculated to be 13 over 28 and minus 15. So we can find out that this number is equal to 26 minus 15, which is 11. So the final answer is B, 11. And we're done. All right, so are there any questions for this problem? I don't see any questions. If you have any, you can ask in the chat or out loud. Either's fine. All right, so next we'll move on to problem 24, which is a geometry problem. So we have a triangle ABC and a point D that divides the side AC so that AD to DC is equal to 1 to 2. All right, so let E be the midpoint of BD and F be the point of intersection of line BC and line A. And we're given that the area of ABC is 360, and we want to find the area of EBF. What are Chevians? So, okay. Somebody mentioned in the chat the words Chevians, and a Chevian is a line segment that connects a vertex of a triangle to a point on the opposite side of the triangle. So when we see a lot of these Chevians, one thing we can do is to use Menelaus theorem. So in this problem, we're going to use Menelaus theorem on triangle BDC and transversal. A transversal is a line that passes through other lines. So in this case, we're going to use the transversal AEF. And what Menelaus theorem says about this triangle and this transversal is that the ratio, or rather the product of ratios, BE over EG. So we're going from here to here, and then here to here, times DA times AC. So we're traveling from here to here, and then from here to here. And then times CF over FB. We're traveling from here to here, and then from here to here. The product of these three ratios is going to be -1 if they're directed. But in this case, we're just dealing with lengths, so we can write 1. All right, so we're told that AD to DC is equal to 1 to 2. So what this means is that DA to AC is equal to 1 to 3. So we can replace the second expression, the second fraction, with 1/3. And then as for BE over EG, we know that E is the midpoint of BG. So this fraction is just 1. And CF over FB is unknown. So what we found here is that CF over FB is equal to 3. So once we know CF to FB, we've basically found another fraction or another ratio in this problem. So how are we going to use this? So now we know that these two are equal since it's the midpoint, and also that if this is B, this is 3 times B. We're given the area of triangle ABC, and we want to find the area of triangle BEF, or EEBF. So one way you can find the area of BEF is by taking the area of triangle BDC and multiplying it by 1/2 and then 1/4. So where this comes from is we're multiplying by BE over BG, and then also multiplying by BF to BC. So BE to BG is A to 2A, which is 1/2, and BF to BC is 1/4. And rigorously, we can basically, what we're doing here is that we're connecting GF, and we're saying that triangle BEF is going to be, its area is going to be half of the area of BGF, and then that is it's going to be half of a quarter of the area of BGC. And that's where this expression comes from, this equation. And so now we have this. And then we can bring back these lengths. So AG to GC is 1/2. What that means is that the area of triangle BDC is going to be 2/3 of the area of ABC by area ratios. And so we have everything we need here, and we can calculate. So this will give us a final answer of 30. So the answer is B, and we're done. So this is problem 24 of the 2019 AMC 8. If there are any questions, please feel free to ask them in the chat. All right, so since there are no more questions, we can move on to the last problem, the final problem of the 2019 AMC 8. So in problem 25, we have Alice, who has 24 apples. And we want to find how many ways she can share them with Becky and Chris so that each of the people has at least 2 apples. So on this problem, yeah, somebody mentioned it. It's helpful to use stars and bars. So here, we're making, we have somebody who's sharing apples with 2 people. So we're going to split these apples into 3 groups. One of them goes to Alice, one of them goes to Becky, and one of them goes to Chris. So we can write the number of, we can denote the number of apples that Alice gives to herself as A, and then the number of apples that she gives to Becky as B, and then lastly, the number of apples she gives to Chris as C. In this problem, she has totally 24 apples. Yes, the answer is C. The only other condition that we're given is that A, B, and C are all greater than or equal to 2, because each person gets at least 2 apples. So now we want to find the number of ways we can get 3 numbers A, B, and C to add up to 24, and all 3 numbers are at least 2. So to find this number, we're going to use stars and bars. But first, we're going to give all of these numbers a correction. So since A, B, and C are all greater than or equal to 2, that's kind of weird, and we don't like that if we're going to use stars and bars. So in fact, what we can do is we can kind of like change the numbers a bit so that each of them is greater than or equal to 1 instead of 2. So we're going to nudge all of these numbers a bit. So we're going to subtract all 3 numbers by 1 and get our new set of numbers A prime, B prime, and C prime. Those are what we're going to call them. So let's rewrite both of these conditions in this new set of variables. So A prime, B prime, and C prime are all greater than or equal to 1, and A prime plus B prime plus C prime is equal to 21. So now we can use stars and bars to find the total number of ways we can get A prime, B prime, and C prime so that they're all greater than or equal to 1, and they sum to 21. So the way we do this is we're splitting 21 into 3 groups of at least one thing each. So we have 21, let's say, stones or bars. So 21 of these, and we're splitting them into 3 groups. So we're going to insert 2 bars or sticks. Yep, we're going to insert 2 bars or sticks into this this collection or this row of stones or bars. Stones. We're going to insert 2 of these sticks or bars. We're just going to call them sticks. We're going to insert 2 of these sticks into this collection of stones. And now what we have is that we've divided these 21 stones into 3 parts. The first part is determined by where the first stick is. The second pile is going to be between the first stick and the second stick, and then our last pile is going to be the pile that's after the second stick. So that is this part. And we want each of these piles to have at least 1 stone. So what that means is that we cannot have any sticks directly next to each other. So we can't put 2 sticks between any given 2 stones. And also we can't put any sticks at the end, because if we put a stick at the end, we're going to have a group of 0 stones, which is not what we want because of this condition. So we want to insert 2 sticks into this pile of stones without while making them not at the ends and also not between the same 2 stones. So in total there are 23 positions, or sorry, 20 positions, since there are 21 stones. There are 20 positions where we can put a stick. And we're going to choose 2 of these positions, and these 2 positions must be different. So, for example, we can put 1 stick here, 1 stick here. Those are the 2 positions that we chose. And there's going to be 20 choose 2, which is equal to 190 ways to position these two sticks. And so there are 190 ways to choose A prime, B prime, and C prime, and also then 190 ways to choose A, B, and C. So 190 is the total number of ways that she can share these apples with her two friends. So the answer is 190, which is C, and we're done. All right, so if there are any questions, you can ask. And if there are no questions, we can move on to the next year, which is 2018. Why is it 22? All right, so here, once we have all these stones, we want to pick two positions for the two stones, two positions for the two sticks that divide the stones into 3 regions. So we're going to take two of these 20 positions to place a stick, and we want these positions to be different because we cannot have two sticks between the same two stones. So there are exactly 20 positions to put a stick, and we want to put two sticks in these 20 positions. So we're choosing two positions from the 20 to place the two sticks. And the number of ways we can do that is 22 2. So our answer is 190. Yeah. All right. So next up, we have the 2018 AMC 8. So in problem 22, we have a square ABCD and also a midpoint of side CD, which is E, and also the intersection of BE and AC, which is F. We're told that the area of quadrilateral AFED is 45. And we are asked to find the area of ABCD. So in this problem, we want to find a relationship between the areas of quadrilateral AFED and square ABCD. So in order to do this, what we can do is we can use some area ratios. So, for example, one thing we can do is we can write the area of ADEF, which is what we know, in terms of the area of ADC, sorry. So this is equal to ADC minus EFC. And so we can rewrite EFC as some area ratio between EFC and ADC, and then times the area of ADC. So we want to find that ratio. So before we find that ratio, we need a few lengths. Let's say this is K, this is K, and then this is the area of 45, this is 2K. So before we get on into all of these area ratios again, we're first gonna use a similarity between two triangles. Yeah, some of you have already wrote this in the chat. So triangle EFC is similar to triangle BFA, and therefore we have these length ratios. So FC over FA is equal to EC over BA, which is equal to K over 2K, which is a half. So from here, we can suppose FC has length L, then AF has length 2L. And now we have more length ratios. And now we can right? ADF again, as we have before, now that we have more information. ADC minus the area of triangle EFC. And then we can notice that the area of EFC, in terms of the area of ADC, is just, here we have a half, which is CE over CD, times a third, which is CF over CA, and then times the area of ADC. And so now we have 5/6 times ADC, the area of ADC. Okay. So we want to find the ratio of the area of ADEF and ABCD so that we can find the area of ABCD. So once we have the area of ADEF in terms of ADC, we can furthermore write it in terms of ABCD. So we can write this as 5/6 times 1/2 times the area of ABCD, which is equal to 5/12 times the area of ABCD. And since we know that the area of quadrilateral AGEF is 45, this equation just amounts to this. 45 is equal to 5/12 times ABCD. And from here, we can calculate the area of ABCD to be 108. And that is answer choice B. So the answer is B, and we're done. All right, so are there any questions? If there are no questions, we can move on to the next problem. All right, so, okay. Right, so what motivates this whole idea is we want to find something that relates what we want to find and what we're given. So we want to relate the area of AFEG to the area of ABCD. And that's what we're doing with all of this area ratios. All right, so that's it for problem 22. The answer is B. And if there are no questions, we can move on to the next problem. Okay, so next up we have problem 23. So in problem 23, we're given a regular octagon, and we're taking 3 points, 3 randomly chosen vertices of the octagon, and then we're making a triangle with these 3 points. We want to find the probability that at least one of the sides of the triangle is also a side of the octagon. All right, so since we're dealing with probability, one thing we can do is to start by finding the total number of possibilities, to like choose 3 points and form a triangle. And this number is just 8 choose 3, which is 56. Since we're choosing 3 of the vertices from the 8 to form a triangle. And so we want to find the probability that at least one of the sides of the triangle is also the side of the octagon. So when you see this, the thing that we want to find, you might think that it may be easier to find, to count what's not given by the problem statement. So like, it might be easier the probability that none of the sides of the triangle are also a side of the octagon. So what we're doing here is, again, we're taking the complement and we're finding that. So let's try to find the probability that none of the sides of the triangle is also a side of the octagon. And at the end, we want to remember to subtract this probability from 1, since we're finding the probability that the opposite of what's asked is happening. So to find this probability, we want to find the number of ways to choose 3 points and form a triangle that does not have any edges on the sides. For example, this is one of the triangles. So one way to count this is we can consider the number of vertices, the number of edges that each edge out of our triangle kind of like goes through, sort of. So for example, this edge goes through 3, it cuts off 3 of the vertices, or sorry, 3 of the edges of the octagon. And this edge cuts off 2 vertices, sorry, 2 edges of the octagon. And lastly, this edge cuts off 4 edges of our octagon. So we can consider the number of edges that each edge of our the number of edges of the regular octagon that each triangle side cuts off. So if you consider this, you can notice that in order to cut off all 8 edges of this octagon, we can partition 8 into 2 possibilities for the number of edges cut off by each side. And these 2 possibilities are 2 plus 3 plus 3 and 2 plus 2 plus 4. So what 2 plus 2 plus 4 means is we're taking a vertex and we're cutting off 2 on this side, cutting off 2 edges on this side, and then cutting off 4 on this side. So we're going to have a triangle that looks like this. And there are 8 possible triangles that look like this by just rotating this triangle around the octagon. So that gives us 8 cases for our first case, 8 possibilities for our first case. And for our second case, we have a triangle that looks like this. And the number of triangles that look like this is basically the number of ways, is basically the number of rotations this triangle can get. So we can rotate this triangle around the octagon similarly to how we rotated our first triangle. And there are going to be 8 ways to have a triangle that looks like this. So this gives us a 16 total ways to have none of the sides of the triangle being a side of the octagon. What are 2 plus 2? Okay, so these are the 2 possibilities for basically given any triangle. Let's say this is a triangle. Each edge of the triangle cuts off some sides of the octagon. So for example, this triangle side cuts off these 2 edges of the octagon. And then this side cuts off these 3. This side cuts off these 3. So here we're having 2 plus 3 plus 3, which are basically the number of edges of the octagon that each side of the triangle cuts off. So this side cuts off 2, and these 2 sides cut off 3 edges of the octagon. And the other possibility is 2 plus 2 plus 4. And these are the only 2 possibilities because since none of the sides of the triangle is also a side of the octagon. Each of the sides of the triangle must cut off at least 2 edges of our octagon. So we can't have anything like this. So yeah. All right. So now we can calculate this, and we're going to get a final answer of 5/7, which is C. Okay. All right, so I'm not seeing any more questions, so we can move on to our last 2 problems, 24 and 25. 24 is a problem about a cube. So in this problem, one thing we want to do is we want to find what this region is. Since we have this very strange cross section, we want to find what shape it is. So we can ask ourselves, what is the shape of this quadrilateral? And so one thing you can notice is that since J and I are midpoints of their respective edges, in fact, what we have is that JC, JE, EI, and IC all have the same side length, all have the same length. And this length is equal to √5/2, or rather √5/2 times the side length of this cube. And so what we found is that this rhombus, or this quadrilateral, is a rhombus, since all 4 of its sides have equal length. So one property we know about the rhombus is that its 2 diagonals are perpendicular. And in fact, the area of a rhombus is equal to 1/2 times the area, 1/2 times the product of the lengths of its 2 diagonals. And we can find that we can find each diagonal's length. So for example, in this picture, EC is a space diagonal of this unit cube, or of this cube. So in fact, the length EC is equal to √3 times the side length of the cube. And we can also find the length of IJ in terms of the side length of the cube. IJ has the same length as FH, which is a face diagonal. And the area, or sorry, the length of this face diagonal, FH, is equal to √2 times S. So we've written both of these in terms of S, and now we're ready to find the area. So we can plug these both in to get that this area is equal to 1/2 times √6S squared. We want to find the ratio of this area to the area of one of the faces of the cube, which is S squared. So in fact, this ratio is equal to √6/2. So what this leaves us is to find the square of R, from which we can get the answer 3/2. So the answer is C, and we're done. So, okay. That's it for problem 24. Are there any questions? We've got one more problem to go, and that is of the 2018 AMC 8. And this problem is right here. So this problem asks, how many perfect cubes lie between 2 to the 8 plus 1 and 2 to the 18 plus 1, inclusive? So first, we can notice that actually neither of these are cubes. If we want to find the number of perfect cubes that lie between 2 to the 8 and 2 to the 8 plus 1 and 2 to the 18 plus 1, what helps is to find the smallest cube that lies between these two numbers, and also the largest cube between those two numbers. So the smallest cube that's greater than or equal to the 8 plus 1. Well, first we can calculate 2 to the 8 plus 1 to be 256 plus 1, which is 257. And so the smallest cube that's greater than this is 7 cubed. And so what we want to do here is we're going to take note of this. 7 cubed is our smallest cube. And then we want to find the largest cube that's between these two numbers. And this is not too hard because 2 to the 18 is equal to 2 to the 6th cubed plus 1, which is 64 cubed plus 1. So our largest cube between these two numbers inclusive is 64 cubed. And all cubes in between these two numbers are also between 2 to the 8 plus 1 and 2 to the 18 plus 1. So the total number of perfect cubes between these two numbers is 64 minus 7 plus 1, which is 58. And that is our final answer. So this is the final problem of the day. Are there any questions? Sure. I can go back to these two problems to show you. All right, so I'm going to move to problem 24's slide in around 5 seconds. All right, moving on to this slide. I'm going to wait 10 seconds more on this slide. And then lastly, this is problem 25. It's pretty short, as you can see the solution. And all right, so those are all of the problems we're going to be going through today. Thank you all for joining. And of course, feel free to attend any more Logistem workshops. And of course, thank you for attending today's Logistem math workshop. So any more information on these math workshops or math workshops or any workshops in general can be found on our website, logistem.club. And yeah.
Thank you.
I hope you all learned something new today. And thank you all for joining. Hope to see you all soon. Bye.
Thanks. Bye.
Thank you. Bye.
Thank you. Bye.
Happy New Year, everyone.